Okay, want to write acceleration for A and acceleration for B. Okay. For B on top of friction force, nothing here. I should just, yeah, just F on I direction.
And for A, the tension force and applied force, those don't count. Arrows, okay?
Oh, yes. Good catch. Yep, that's a good one since I saw some of mistakes in exams. When you already have vector form, vector notation there, on the other side, when you have the unit vector, you shouldn't add that vector notation. Here it should be just F. Okay. Right, step 4, write acceleration. So for A, we have AA equals AAI. For B, we have AB equals ABI. Okay, then step 5, we want to assemble all the equations together, right? Same deal here. We want to assemble the equation for A, assemble the equation for B. So let's do a practice here. If we assemble the F equals MA, that's for AA. Sum of forces equals M. Okay, this is MA and BAB. Okay, when you assemble equations, F equals MA, let's look at the mass A. All that forces must come from the forces acting for your block A, from your step 3, just for A. So we can assemble all the forces there. Okay, I think this is something is different. When we have multiple masses, multiple blocks, you want to do everything separately for mass A and mass B. Even when you assemble equations for F equals MA, you do the same thing. You do not mix them. If you mix them together for F equals MA, you're going to confuse yourself. So do that separately for mass A and mass B. The rest of the work, it's just substitute all the vector forms for forces and accelerations, then build scalar equations, right? Okay. Any question on this example? We're going to stop here. Like I said, we won't solve everything for you. Krista?
For A, is that A that you wrote right there?
Yeah, it's a sum of the forces equals MA times AA.
Yeah, just below it looks like a B. I'm not sure if I'm reading it right.
Here?
No, like that.
Oh, yeah.
Yes.
Good catch. My bad. That's A. Yeah. Make sure it's consistent. Everything's for A. On this side, everything's for B. Okay. You good? That will give you practice. If you see multiple masses, this is how should you do it. Okay, now let's move on to a different example. I think on your homeworks, we have a problem that you have 2 masses. All right, now let's look at another example. This is for a 13. So here we have a arm. This arm, it's pinpoint at point O. Let's call this arm OA. It's pinpoint at point O, which means it can only rotate about point O. And on the top of this arm, we have a block P. The block P is sitting on top of that arm, and there's some friction coefficient between that block P and the arm. And we know the coefficient of friction is mu s. And this arm, it's rotating. This is counterclockwise with a speed omega, and that omega is constant. And we also know the distance from O to P, that block, R, here the distance is 3 feet. And so as this arm rotates counterclockwise, the angle gradually increases, right? So at one point, when the angle becomes large enough, then this block starts to sliding down to the arm. So we know that angle theta, the block start to slip, it's 53.15 degrees. And here we're trying to find out what is that friction coefficient, mu s. So we have s here, that means that's a static friction coefficient. That's a friction coefficient when you use under things are not moving. Do everybody understand this problem? So this block is sitting still on that arm, but when the angle is large enough, angle theta is large enough, everything starts sliding down. And we're trying to find mu s. Okay. Even it's asking for different things, you can still use the 6 steps to solve this problem. First, try to draw the free body diagram. Here, looks like we have 2 masses. We have arm OA and block P, but what is really matters is that block P, right? So that arm doesn't really do much. So you only need to do the free body diagram for block P. Step 1, free body diagram for block P. So how many forces should be on your free body diagram? Always have weight force, WP. Always have normal force. And normal force should perpendicular to the surface. It's called M. Let's call that MP. And in this case, we should have another force, friction force, to prevent that block P sliding down. So P, block B is going to sliding towards to O. That has that tendency to sliding down to O. So the friction force should preventing that motion. That's FF. Okay, this should be the free body diagram. You should only have 4 forces. And let's look at how to set up coordinate system. How would you like to set up coordinate system for this problem? Which direction you would like to set up? And keep that in mind. Eventually, we want to, in step 3, step 4, we want to write a acceleration equation for block P. So if look at that problem, which coordinate system would be easier to use to set up your acceleration? You have a block is rotating at certain omega and certain angle. You know the distance r from origin to that point. Which coordinate system would make sense? polar. Yeah, polar coordinate system would be a good choice here. So if we want to use polar coordinate system, how would you set up your coordinate system? ER and E theta. Which direction should be your ER? Which direction should be your E theta? ER should be the direction pointing to the particle from the origin. So in this case, always the origin, particle pointing to particle P. This is ER hat. E theta should be perpendicular to ER, pointing to the increasing angle of theta. Remember that? Here we're rotating counterclockwise. So the increasing direction of theta is going up, E theta. That's our coordinate system. Okay, now we have coordinate system set up. Can we start to write out all the forces in vector form? Just keep them. Remember this? Here my drawing is a little bit off, but your E theta should have the same direction as your arm. Okay, so now let's write all the forces. The friction force gonna be FF on positive ER direction. MP, the normal force is on positive E theta direction. Yeah, I'm making that mistake again here. Okay. However, your WP, it's angled based on your coordinate system. You have to use that angle theta to project your weight force into ER and E theta direction. You will need to use trigonometry, right? So in this case, if you are not sure how to do that, make sure you do more practice off class. So here should be mg sine theta on ER minus mg cosine theta on E theta. So that's all the forces. Step 4. Okay. I think step 4 is definitely the interesting part of this problem. Acceleration. How would you write acceleration equation for that particle, for that block P? We already set up the polar coordinate system. What is the acceleration equation under polar coordinate system? That requires you to check your notes. Chapter 1, what is the equation for polar acceleration? So A, acceleration equals to R double dot minus R theta dot square ER plus R theta double dot plus 2 R dot theta dot E theta. Okay, so look at this equation. Actually, we know a lot of things here. What is R dot? R dot, it's simply just equals omega. Omega angular velocity or angular speed, it's theta dot. Theta is just the angle. Theta dot means how fast that angle is changing. That's the angular speed. And theta double dot is simply just omega dot, right? And in this case, we know omega is a constant. So if you see theta double dot, that will give you 0. It's just given condition for this problem. Omega equals 2 radius per second constant. And also, if that block P is not moving, the distance from O to P is fixed, is R. So R dot gonna be 0. So r dot, it's also 0. A. So that tells you your acceleration, only left with just A equals r double dot. That's also 0 too. It's going to be negative r times omega square er hat plus 0 e theta hat. Okay. Once you have the acceleration in vector form, I believe you can do the rest. Assemble the equation F equals ma and break them down to scalar equations to solve unknowns. Okay. But the tricky part is if you can identify, it would be easier to use polar coordinate system to describe the acceleration of that block P. So far we had path coordinate system, polar coordinate system, right? So that tells you in this chapter, you're gonna use different coordinate system to solve, to find accelerations. Okay, any questions about this example? Great. Let's do, okay, one more. We have two more, but let's look at this one. For A4. All right, this example, we have a car is moving on a surface, on the floor. It's moving to the right with the acceleration A. Inside of that car, there's a slide. There's a smooth slide. And P here is a collar that can slide on that slide freely. And we know that slide has that angle theta. And block P has a certain mass m. And we also know the theta angle. We know A is constant, is acceleration. Here, what we're trying to do is imagine if you're moving that car at a certain acceleration and that block P gonna be just stay at that precision without sliding up and down. So we're trying to find out what is the required acceleration for that car to keep that collar P from sliding. I want you to maybe take 1 minute to digest what is going on in this problem. Imagine that you have a car, you have a slide. When you push that car, that slide, the collar will stay at position if the pushing force is is enough. It's kind of like the race car problem we did. To keep the race car on the roadway without sliding, right? You have to keep a certain speed, a certain acceleration. It's the same deal here. Yeah, let's try to use 6 steps to set up this problem. Step 1, free body diagrams. Here, what we care, it's the only thing we care is that particle P. So you only need to have free masses, free body diagram for that P. And also another trick here. Even looks like we have particle P and that car, and you may think, okay, we have 2 masses, we want to have 2 free body diagrams. But here's the trick. If you look at the problems, mass m is only given for the collar P. It doesn't even tell you what is the mass for the car. That's kind of the hint. You don't need to care about that car. Just draw the free body diagram for particle P. So P gonna have a weight force, W, a normal force from that slide, N. And any other forces? Free body diagram for that quarter P. Any other forces should be on your free body diagram. That's it? Just N and W? Do we have friction force? No. It's smooth, so there's no friction. That's it. You only have two forces. Now let's set up coordinate system. How to set up coordinate system? Either way, you can use just I and J like this, or you can put I and J in an angle. Either way, I think in this problem doesn't matter which way. We're gonna just use straight up J and the horizontal I. Okay, now you have step 1, 2. Step 3 is to write everything in the forces in vector form. We'll only have two forces. Should be pretty easy. Normal force has an angle, so you use trigonometry and N sine theta, that's on I direction, plus N cosine theta on J. For your weight force, it's pretty easy, straight down, which is negative mgj. That's step 3. Step 4. So write acceleration. In this case, acceleration should be A equals something I plus something J. Here we don't really have a path coordinate system or polar coordinate system. I think Cartesian is more than enough to describe the acceleration. So my question is, so acceleration A should have both I and J components. So which components, on which direction acceleration should be 0? Read the problem again. Our goal is to keep that quarter from sliding, which means we want that quarter P to move with the car, but without moving up and down. So if our goal is to keep that quarter from moving up and down, that means there's no motion, should be no motion on J direction. But since the whole car is moving to the right, the quarter P must move to the right as well with the car. So that tells us the acceleration for that quarter should have A on J on I direction, but 0 on J direction. You can make a note that's no motion on J. Okay. So this problem actually is pretty simple. Now you have all the forces and acceleration. Step 5 to assemble F equals ma. And you should able to solve for A. Okay, wow, did pretty good. One more example. Any questions on this example? Keep the color, stay at position. Now we have 5 minutes left. Try your best to set up this problem. It's a 4A4 example. It's a cable car problem. We know the mass of the cable car. We know the forces that is dragging the cable car. And we want to find out what is the acceleration for the cable car and what is the forces acting on the cable that's from the cable car. I believe now you have so many practice, you should able to set up free body diagram coordinate system for this one. Okay, check the free body diagram to see if you have three forces on your free body diagram. All right, raise your hand if you get that part right. Three forces on your free body diagram. Very good. Okay. Okay, now try to write forces in vector form. Leave FC blank to test your skills on how to resolve the forces on I and J direction. Okay, this problem, the angle theta is not given directly. Instead, it tells you the number 12, 15. That's just a different way to tell you what is the angle of that theta. Triangle like this, you can find out the other side. The hypotenuse is going to be 13. So you can use that information to resolve all your forces. FC is 5 over 13 times FC negative on I direction. It's FC times 12 over 13 positive on J direction. That's all the forces. For your acceleration, it's the same thing. Your acceleration AC, remember, right now the cable car is moving both to the I and J direction. The last example we did, the color stays on only on I direction. There's no motion on J direction. But this cable car is moving on both directions. So AC has both components, I and J. And same thing, you want to use that angle to resolve what is on I and J. So for on I, we have 12 over 13. On J, we have 5 over 13. Okay, the rest of the work should be easy. Assemble equations, solve for unknowns. All right, we did pretty good. We went through like 4.5 problems example. All right, tell me how do you like it? Give me a thumbs up. You think that's good? Give me a thumbs down if you think that's too much. Okay. All right. Okay. Great. All right. Thanks. That's all we have today. And have a good weekend.